A new study has confirmed that the Earth is encased in a massive bubble. Better said, the entire solar system is encased in this massive bubble. And no, it's not one of those bubbles we used to blow as kids, nor is it a matter of water and soap. In reality, it is much larger. To put it simply, if you had the opportunity to drive your car at the speed of light and opted to cross this bubble, it would take you over 1,000 years at the speed of light. Furthermore, the boundaries of this bubble influence the formation of all neighboring young stars. A new study reveals exactly that. But where does this bubble originate? Will it eventually vanish? Is this a trait unique to the solar system, or do different star systems have different bubbles? Follow along in this video to find out the answers to all of these questions. Let's get started. To be clear, the existence of such a bubble has been known for decades. It's been dubbed the local bubble by astronomers. It's a vast emptiness encircled by thousands of new stars. Some investigations were conducted, but this is a difficult topic, and as a result, much remains unknown about this bubble. For example, we have no idea how big it is. According to some estimates, it should be around 1,000 light years across. We're not even sure if this bubble is a perfect sphere. Indeed, it appears to be irregular in shape. It appears to be smaller in the galactic plane, becoming slightly egg-shaped or elliptical, and may broaden above and below the galactic plane, becoming shaped like an hourglass. However, scientists have just discovered that the local bubble may sustain star formation. What happened was that scientists discovered several star-forming regions on the surface of the bubble. According to Catherine Zucker, an astronomer at the Telescope Science Institute in Baltimore, we stumbled upon this discovery completely by chance. In essence, they were extremely fortunate. But before I get to the study's findings, I'd want to explain how scientists believe such bubbles form in the cosmos. The fact is, everything starts with a cute star. This star matures with time, and she is unlucky enough to go supernova. A supernova is a wonderful phenomenon to observe for anyone on Earth because it can reach tremendous luminosities. A supernova can be so intense that its light is comparable to that of a full moon. Supernovae are stars that suddenly become extremely brilliant, outshining their home galaxies. They achieve this brightness in a matter of hours and fade in a matter of weeks to months. Scientists classify supernovae based on their radiated light characteristics, known as spectra. These reflect what components the original star generated and hence released into space when it burst. Type 1 supernovae. Their spectra indicate a lot of carbon and relatively little hydrogen. Astronomers believe this sort of explosion is caused by a white dwarf that has accumulated too much material to resist internal pressure. Type 1b supernovae. Their spectra contain very little hydrogen, but they do contain helium. Scientists believe this type of supernova is caused by the death of a star with a mass at least 25 times that of the Sun. Type 1c supernovae. Their spectra include very little hydrogen or helium, and they develop in the same way as a Type 1b supernova. Type 2 supernovae. The spectrum of this type of supernova contains a lot of hydrogen and helium. Astronomers believe this kind is caused by the demise of a star with a mass greater than 8 times that of our Sun. A star of this type can fuse elements up to iron. A supernova remnant is what remains after a supernova explosion. The supernova remnant is surrounded by an expanding shock wave and is made up of ejected material from the explosion as well as interstellar material that it sweeps up and shocks along the way. A massive star may run out of fuel, ceasing to generate fusion energy in its core, and collapse inward under the force of its own gravity to form a neutron star or a black hole, or a white dwarf star may accrete material from a companion star until it reaches a critical mass and explodes thermonuclearly. In either case, the resultant supernova explosion expels most or all of the star material at speeds up to 10% the speed of light, or around 30,000 kilometers per second. Because these speeds are quite high, a strong shock wave forms ahead of the ejecta. This raises the temperature of the upstream plasma to millions of degrees Celsius. The shock slows down over time as it sweeps up the ambient medium, yet it can expand for hundreds or thousands of years and tens of parsecs before slowing down to the local sound speed. SN 1987A, a supernova in the Large Magellanic Cloud discovered in February 1987, created one of the finest studied young supernova remnants. Another example is the so-called Crab Nebula. Aren't they beautiful? What we believe about these bubbles in the cosmos is that their very sparse gas, as seen in our local bubble, is the product of supernovae that detonated during the last 10 to 20 million years. The gas remains excited and emits in the X-ray range. Geminga, a pulsar in Gemini, was once thought to be the remnant of a single supernova that created the local bubble, but multiple supernovae in the Pleiades moving group are now thought to have been responsible, forming what is known as a remnant supershell. So, effectively, our solar system is encircled by what are assumed to be the remaining Death Stars. The study's goal was to map out the important sites in the solar system's galactic surroundings. The positions, forms, and motions of dense gases and newborn stars within 650 light-years of the Sun were studied by scientists. Zucker and her colleagues used data from the most recent Gaia data released to achieve their goal. Gaia is an ambitious endeavor that attempts to uncover the galaxy's composition, creation, and evolution. It will give unparalleled positional and radial velocity measurements with the accuracies required to generate a stereoscopic and kinematic census of about 1 billion stars in our galaxy and the local group. This represents around 1% of the galactic star population. This massive stellar census will offer the data required to address a wide range of fundamental issues about the formation, structure, and evolutionary history of our galaxy. Gaia, for example, will determine whether stars are remnants of smaller galaxies that were swallowed by the Milky Way long ago. It will investigate the distribution of dark matter, the invisible substance assumed to keep our galaxy together, by monitoring the large-scale motion of stars in our galaxy. The study involves mapping 3 spatial dimensions, 3 motion dimensions, and a time dimension. In fact, the universe is tridimensional, and stars and gas can move in all directions, implying that they can have velocity components in X, Y, and Z. And time was needed because we intended to reconstruct the growth of the bubble and, more broadly, the evolution of star-forming areas across millennia. This had never been done before. Of course, we had some grasp of it, but most studies were based on static 2D views of star-forming areas, which meant they weren't particularly typical of reality. One interesting feature of the stars in these star-forming areas is that they remember where they originated from. Would you like to know what it means? Alright, the amazing thing about a star is that it doesn't forget its origins. They know exactly where they came from, and this information is documented in physics law and measurements. Thus, examining the motions of these young stars aided scientists in reconstructing the sequence of events that led to the formation and expansion of the local bubble. They noticed that these stars were mostly migrating away from the bubble's surface, implying that they were moving because the bubble was growing over time, similar to how a balloon expands when inflated. According to our knowledge, the local bubble is still expanding at a rate of 6.7 kilometers per second. When we contemplate occurrences in space, this is rather a slow speed. The researchers discovered that roughly 14 million years ago, a series of about 15 cataclysmic stellar explosions known as supernovae began near the heart of the local bubble. The supernova explosions triggered a shock wave, and this expanding shock wave subsequently swept up a shell of dense, cool gas, that is, the surface of the local bubble, which has now collapsed to form thousands of new stars, Zucker explained. But why is the solar system in the midst of the local bubble? That is entirely attributable to chance. The solar system was quite far away when the first supernova occurred. However, the solar system's journey around the galaxy landed it in the middle of the local bubble by happenstance. The fact that the Sun is currently in the center of the local bubble implies that similar superbubbles may be common throughout the Milky Way. Otherwise, what are the odds that our Sun is in the midst of one? Essentially, a beautiful analogy might be drawn between the Milky Way and Swiss cheese. Both have holes, and the Milky Ways were blasted out by supernovae produced by dying stars. Scientists are now considering mapping the locations, sizes, and shapes of a larger number of bubbles in our galaxy. Who knows, maybe the local bubble is interacting with other bubbles in our neighborhood right now. However, determining the ages of the so-called supernova progenitors could be a challenging task. The original stars that went supernova are known as supernova progenitors. Because of the shock and conservation of angular momentum, and depending on the orbital parameters of the progenitor, supernova remnants can be detected far distant from where the explosion actually occurred, complicating our task. Gaia data release 3 from the Gaia spacecraft will undoubtedly help, as it will reveal 3D space movements for 30 million stars, a critical component in fitting together this puzzle. This video ends here. Thank you for tuning, everyone. What are your thoughts on the local bubble? Let us know in the comments section below, and I'll see you next time on the channel.